Hey there, geometry. Lesson 4, proving the area of a disk. It's a tad bit challenging, but it's really, really interesting, so I wanted to go ahead and try to push through it. There'll be just a few nuggets of information that I really need you to understand, and the rest of it, you can just follow along and see if it'll make sense to you, but it's just really, really interesting. So first of all, let's sort of set some groundwork here. I've got a circle with a hexagon inscribed. That means it's inside of the circle. And the circle has a radius of r. You see right here. Radius of r, because it goes from the center out. Hexagon has 6 sides. So find a formula for the area of the hexagon in terms of the length of a side, s, and the distance from the center to a side. So if I have 6 congruent triangles here. So 6 triangles, I can do the area of one of those triangles. So the area of one of the triangles is 1/2 times base times height. Now, I have 6 of them, so the area of the hexagon is going to be 6 times 1/2 base times height, right? That simplifies to 3 times base times height. So the area of the entire regular hexagon, which is 6 triangles, is represented by 3 times s times h. All right, let's see if we can take it a step further. You just found the area formula for the hexagon. Now we're going to work through steps to write an area formula of the hexagon using its perimeter, right? So I've got the inscribed hexagon, and it's divided into 6 congruent triangles. Let's just call the area of one of these triangles T. So I'm just going to say T equals the area of one of the triangles. Okay, so we know that 6 times T equals 6, this is what we did, 1/2 SH. So 6 times the area equals 6 times 1/2 SH. Let's regroup things a little bit. 6 times the area equals 6 times S times H over 2, because that's one side of the hexagon, so that's my perimeter, right? So that equals perimeter times H over 2. So that is the area of my hexagon. Big equal sign is the perimeter times the height of the triangle over 2. Sort of interesting, right? Now what's really cool is I can generalize this area formula in terms of the perimeter for any regular. P would be perimeter for, we'll say P sub n, for any, I wrote and, I said any, regular polygon. I don't know what I'm doing. Polygon. So I can write a generalized area formula. The area given the perimeter would be equal to 1/2, n times the area of one triangle. No matter how many triangles there are, a regular polygon is made up of as many equal triangles as there are sides of the polygon, right? So I can rewrite this. I don't know why I'm writing the wrong things. N times area of the triangle is going to be 1/2 the base of that triangle times the height of that triangle. And again, I'm going to rearrange. So we have N times S times H of N over 2. It's the same as what we did for the hexagon. Okay, this right here is perimeter of any polygon. This would be any polygon, number of sides, times H, however many number of sides, over 2. Okay, we're going to use this. That's why I want you to see it. All right. So before we get into the next example, why are we doing it? Well, it shows, I'm going to write for a while, sorry. I want you to get this though. It shows how to approximate the area of a circle. That's what we're doing today. Using inscribed and circumscribed polygons. Okay, that's what we're doing. So how can we use the ideas we've discussed so far to determine a formula for the area of a circle? I know. You guys know the formula for the area of a circle, but let us work through this, okay? How is the area of a regular polygon inscribed within a circle related to the area of that circle? So we're going to have a starting point for the material that follows. That's why we're doing this. So really, what do you think the regular inscribed polygon looks like as the number of sides increases? So if we inscribed a square, that is P4. If we inscribed a hexagon, do not make fun of my shapes, this would be P7. So the area of this circle versus the area of this circle. Okay? We would take we're approximating by the area of the square. How close are we? If we calculated the area of the square, we're not so close to the area of the circle. If we calculated the area of the hexagon, we're a little bit closer. If we calculate the area of a, octagon, so bad at drawing these, especially 1, 2, 3, 4, 5, 6, 7, 8. If we calculated the area of an octagon, because we just developed a formula using perimeter. Okay, we're getting closer. With each inscribed polygon, we're getting closer and closer and closer to the area of a circle. Okay? Makes sense? That's sort of what we're looking for. If I were doing a 100-sided polygon, yeah, it would look pretty much like a circle, especially with my drawing right now, right? All right, so let's start working on. Begin to approximate the area of a circle using inscribed polygons. How well does a square approximate the area of a disk? Create a sketch of P4, a regular polygon with 4 sides, which is a square, in the following circle. Shade the area of the disk that is not included in P4. That's what I did. You guys can do that on your paper a lot easier than I can on my iPad. So I sketched it on my paper and then took a picture of it and put it in my iPad. So go ahead and sketch that. Part B says create a sketch of a polygon with 8 sides in the following circle. Let's see it. Okay, mine looks pretty good. I'm pretty proud of that one. And you see my shaded part between the polygon and the circle is getting smaller and smaller and smaller. Okay, Okay, so which polygon has the greater area? The polygon with 4 sides or the polygon with 8 sides? Now we're talking about the square versus the octagon. Which one has the biggest area? I would have to say the octagon is going to have more area than the square. Will the area of inscribed regular polygon P16 be greater or less than the area of P8? So we have a polygon with 8 sides and a polygon with 16 sides. Which one's going to have the greater area? The one with 16 sides. That's where our circle, we're going to have closer and closer and closer and closer to the actual side of the circle. These are all supposed to be awesome straight lines. Okay, our area, the more and more sides we get, the closer we are to getting the actual area of the circle. So, the area of a polygon with 16 sides is a better approximation. Okay, I just copied this from the book. If we see here, this is P8. Okay, that's my regular polygon with 8 sides. And this is P16. I don't know if I can point to it accurately enough. Oh, that's not bad. So P16 is closer and closer and closer to the approximation to get my area of a circle. Make better sense? Their picture was really pretty, so I thought I'd put it in there. All right, we noticed that the area of polygon with 4 sides was less than the area of the polygon with 8 sides, and that the area of the polygon with 8 sides was less than the area of the polygon with 16 sides. In other words, the area of Pn is what? The area of P2n. The larger the number of sides, the larger our area is going to be. Okay? So we're using the n polygon to create the 2n polygon. Like when I drew mine, I used my square to create my octagon just by splitting it into more and more pieces, right? So I used my 4 polygon to create my 8 polygon, to create my 16 polygon, etc., etc. Does that make sense? You can't answer me. When we draw the segments, oh, for goodness sakes. That join each new vertex in between a pair of existing vertices. The resulting 2n polygon has a greater area. Than the n polygon. Cool. All right, let's do something different now. Okay, we're going to take it a different way. Okay, now we're going to approximate the area of a disk or circle using circumscribed or outer polygons. So first of all, circumscribe or draw a square on the outside of the circle. Okay, following the circle so that each side of the square only touches the circle at one point. We will denote each of our outer polygons with a prime notation. So this is p prime to the 4th, where when we were on the inside, we were p to the 4th. So bad drawing, but this was p to the 4th versus p prime to the 4th. Now go ahead and try to do p prime with 8 sides. So if you look, it's the same way I drew my other one. Okay, this will be there, cut that there, cut that there, and there. And then you can erase the corner triangles, and you get your p prime to the 8th. And I could draw the p prime to the 8th pretty well, but when it comes to the 16th, not so much, right? So indicate which polygon has the greater area, to the 4th or to the 8th. Well, in this case, 4 side has more area than the 8th. Just look at the shade. There's more shading with the 4 side than there is with the 8th. More shading. Which has a better approximation of the area of a circle, p prime with 4 sides or p prime with 8 sides? P prime with 8 sides is a better approximation. Because it's closer to the shape of the circle, it's tighter in, right? How would the area p prime n compare to the area of p prime 2n? Well, the area, let's use area. The area of p prime n is going to be bigger than the area of p prime 2n. P prime 2n, let's get that lowercase, subscript, can be created by chipping off, by breaking away, by erasing the vertices. Therefore, the area of p prime 2n will always be less than the area of p prime n, always. Because we're breaking away the area of p prime to get to area of p prime 2n. Okay? What I wanted to show you here, and it's pretty cool, so this would be 16 sides, which I can't draw. If you look really, really close into it, we have the circle, and I'll never be able to, the circle is in there, that wasn't very good. The circle is sandwiched in between the two. So we have the inscribed one, and this is actually, the circumscribed one is not pointing to the right, that's on the outside. So you have the inscribed one and the circumscribed one, and the circle is actually sandwiched between the two, which you see right here. It's a really good approximation, right? So the area of the circle is actually less than the area of the circumscribed polygon. The area of the circle is greater than the inscribed polygon. Let me write that down. The area of the circle is greater than the area of the inscribed polygon. Pretty cool. So here we trapped the area of the circle between the areas of the outer and inner polygons for all sides n. Since this inequality holds for every n, where we really have, we can say the area of p to the 2n is less than the area of the circle, is less than the area of the p prime 2n. Okay, that inequality holds for every n, for however many sides we're going to make the polygon. The difference in the areas between the outer and the inner approaches 0 as n goes to infinity. This is an important thing that will you'll need to know as your math gets harder. So as n, the number of sides in my polygon, approaches infinity, the difference The difference means a subtraction between the difference in areas between the outer and inner polygons goes to 0. Gets closer and closer to 0. This is called a limit, which you'll see in a few more slides. Okay, it's a limit, and we use those in calculus, and you'll see them again, but it just means that as one of your variables approaches infinity, something happens to your equation. So I'm just trying to figure out a way to say it. The number that the areas of the inner, I know I just said this, we're going to say it one more time. The inner polygons converge to as n approaches infinity. All right? Okay. So this is sort of fun. Excuse my drawings, I'm only drawing up to a pentagon, but if we calculated the area of the circle with a radius of 1, radius equals 1 for all of them, but we have 3 sides, 4 sides, 5 sides, etc. I can say that the area for 3 sides is going to be 1 point, and it's approximately, hold on, we should make that a wiggly. The area of a 3-sided polygon is approximately 1.299. So these are inscribed polygons in a circle with a radius of 1. The area of the 4-sided is exactly 2. The area of 5-sided is approximately 2.377. The area of the approximate area of a 6-sided, which I didn't draw, there's our hexagon. The circle's a radius of 1, though. The area heptagon, approximately 2.736. A 100gon is approximately 3.139. Do you see where we're going? The area of a 1000th gon is 3.141 pi. Now my radius is 1 for all of those examples. And as my number of sides gets greater and greater and greater, then I'm converging on pi on purpose, because that's how the math works. As n approaches infinity, the limit of the areas is pi. Okay? That's really, really cool. So we have the area of a polygon with n sides is equal to the perimeter of the polygon with n sides times the height of the triangle of n sides over 2. As n approaches infinity, what happens to the height and the perimeter in terms of the radius and the circumference? As n approaches infinity, what happens to the height and the perimeter as n, I would say as n approaches infinity. We just did that. So as n approaches infinity, what happens to the height and the perimeter in terms of the radius and circumference? Remember, circumference is the distance around the circle. I don't know what that says. I have a picture I'm going to bring over here to give you just an idea of what I'm going for. Now, if you look, we have 6 sides, 10 sides, 16 sides. What's going on with our radius and our length of our base and our height? So as our base gets smaller and smaller, as n goes to infinity, the size of this s value gets smaller and smaller and smaller, and the size of the radius compared to the height become closer and closer and closer together. So the base gets smaller, and the measurement of the radius and the measurement of the height get closer and closer and closer to each other. Say that again. The base gets smaller, the radius and the height become closer to the same value. Okay? So I asked you the question, as n approaches infinity, what happens to the height and the perimeter in terms of the radius and the circumference of the circle? So as n approaches infinity, the perimeter approaches the circumference of the circle. I did that twice. And the height approaches the radius of the circle. So the area of our circle is equal to 1/2. Instead of the height, we can write the radius, and instead of the perimeter, we can write the circumference. Since we know that circumference of a circle equals 2 pi r, we can also say that the area of the circle equals 1/2 times my radius times my circumference. So these divide out, and I have pi r squared. We did it. Cool. Okay, this was what I said about the limit. So read through it. I hope I did a better job explaining with more simple words. But this is how our problem set's going to work. So tomorrow we may have to work together a few problems before you get the hang of it. But it's pretty cool. Good work today. I know that was tough.